Let's look at S-CP.A.3 worksheet number 1, all about conditional probabilities and independence. Now, a lesson already kind of covers conditional more in depth, but I'll do a quick little review in case you didn't hit that first. First of all, a conditional statement is often written like this. This would mean, what's the probability of A given that B has happened? So the line is given that B has happened. So this is implying that it's happening second in the order. This isn't just like out of the gates picking a card, okay? This is saying B has already taken place, whatever it was. A card was picked, a marble was selected, a dice was rolled, a spinner was spun. That's already happened. Now what's the probability of A? So let me show you what that looks like in a Venn diagram. So here's what it means. What's the probability of A given that B has already happened? So if B has already happened, basically we know one of these events here has happened. Notice A's gone now, except for this part of A. So the probability of A happening is that intersection, right? This little bit. That's the only way you can get an A now. If B has happened, something in that boundary has happened. The only way for it to be A is for it to be in that intersection. So the chances of A now are the intersection out of all of what B is because it's happened. Now, if that probability right there is the same as the original probability of A, if this is the same, then they are independent. Because think about this. If your conditional probability B has taken place, has happened, and if that simplifies out to be the original probability, then actually they were independent. B didn't impact at all. Now that isn't always the case. Obviously, sometimes this value does not equal the probability of A. But if it does, that actually would mean that they were independent. This is a second test of independence. And actually, let me show you why that would be. Let me simplify this. Now, if they're independent, we learned in a previous lesson that that would be the probability of A times the probability of B. So I make a substitution here. And guess what happens? If they are truly independent, then the probability of A, given that B has happened, is simply the probability of A. This is the second test of independence. The first test was if the probability of A times the probability of B is simply the probability of A and B. If the original numbers produce the intersection, then they were not changed in any way and you're independent. This is an equally powerful way to determine independence, is that if the conditional statement, if A's probability is the same after B has taken place, then they were independent. They didn't impact each other. So a lot like that idea that if I pick from the bag and the marble comes out, if I put the marble back in, the second pick doesn't care what happened previously because it's just the same. If I picked up a dice and I rolled it once and I roll it again, those are independent of each other. The conditional statement would actually just simply be the probability of the original probability. So these two items become a very important idea in what is conditional and how it implies independence. If you're told that they are independent, these two rules can be put into play. And what it allows you to do is to make some decisions about that. So if I said, okay, the two items are independent. The probability of A is 0.3 and the probability of B given A is 0.5. Now, because they're independent, the probability of B is just simply 0.5 as well, because if they're independent, that knowing that A had taken place doesn't impact B's probability, and it would just be that 0.5. And so you're going to use that knowledge to solve some different types of problems. So, or even to determine if things are or are not independent. Let me give you an example. So let's take this guy here. 0.15, 0.1, and 0.3. This is the probability of A and B. Now, the question is going to be, are these independent? Not a bad question. The probability of A is 0.25. The probability of B is 0.4. Now, we have some different tests that we could do here. We could multiply these together, and you can see actually that if I do multiply those together, I get 0.1, which is one of the tests of independence. Those are indeed independent. Now here's another way to test it. What is the probability of B given that A has happened? So what's the chances of getting B now that A has happened? So let's write that down. Probability of B given that A has happened. Well, what that means is A has happened. All right, so here's A, 0.25, and the probability of B is 0.1, okay? And guess what? If you simplify that out, you get 0.4. And so the probability of B is the same as the probability of B given A. So there are now two very important tests of independence. And one is about the conditionality of the relationship, and the other is just simply about the multiplication of A and B to get the A and B, okay? I would also encourage you to understand this diagram. This diagram represents the probability of B given A has happened, because there used to be a B here, but now that we know A has happened, it's somewhere in this zone, and the only way to get a B now is the 0.1 out of the 0.25. A common error students get is they put it over 0.15 or whatever, but remember A or B is the whole region, even the intersection.